In this video, I am going to talk about carbocation stability and carbocation rearrangements. We've already gone through the SN1, SN2, E1, and E2 reactions, and we've kind of gone over the basic idea as well as some things to look out for. In this video, I want to tackle these two topics because they can be some important considerations, especially for the SN1 and E1 reactions. And then after this, I'll release a video on the SN1, E1, SN2, E2 summary, where we can look at all the reactions, compare and contrast them, and then figure out how to determine which reaction is happening based on a given set of conditions. But this carbocation stability and rearrangements, this is important for that. So let's go ahead and get started here. So the first thing we have to consider for carbocation rearrangements is the stability of carbocations. Not all carbocations are made equal, some are more stable than others. And this little series that I have listed right here, this is a good visual example of the typical series that you would see in an undergraduate course. So at the very left here, I have a methyl carbocation. This is the most unstable. And way at the right, I have this tertiary carbocation that is the most stable. So I have a stable and an unstable carbocation, and this is going in order of increasing stability. So a primary carbocation right here is more stable than a methyl carbocation, secondary is more stable than primary, and tertiary is more stable than secondary. So we are increasing stability as we go this way. Now there is an important thing to recognize here. That is that the stability is increasing with the more R groups that we have. Okay, stability is increasing with each additional R group. So if I look at this methyl carbocation, it's just CH3+, I don't have any R groups. But if I add one R group and I make it a primary carbocation, now it's a little bit more stable. I do the same thing and I make it a secondary carbocation, it's then a little bit more stable, and I add a third R group, now it's even more stable. So the presence of R groups, alkyl groups, makes carbocations more stable. And we have a term for this. We call it hyperconjugation. Hyperconjugation. And this is precisely this exact phenomenon, that more alkyl groups equals more stability. So if I have, for instance, a carbon atom with 3 methyl groups as opposed to a carbon atom with only 1 methyl group, the carbon atom with 3 methyl groups and that carbocation is going to be more stable because it has more of those alkyl groups. And that phenomenon is known as hyperconjugation. The idea is basically electron donation. These R groups, even though they don't have lone pairs, they have enough electron density to push some of that towards that carbocation and stabilize it just a little bit more. So hyperconjugation provides a reasoning for why we have this increasing trend in carbocation stability, and this is important especially for the SN1 and E1 reactions, because we're going to encounter carbocations, and we need to be able to determine, depending on how stable the carbocation is, whether or not that reaction is going to take place. So the other thing that this is useful for are these carbocation rearrangements. The phrase rearrangement in organic chemistry can sometimes be a little bit jarring for students. A rearrangement reaction in general is just any reaction where the molecule sometimes literally just breaks apart, shuffles itself around, and then puts itself back together. Okay? And the driving force behind most rearrangement reactions is stability. Okay, the driving force is stability. And this is important because a rearrangement reaction almost always happens to make a molecule more stable. So if I have a molecule, I'm doing a reaction, and I have an intermediate that is not very stable, but it has the capacity to rearrange itself and become more stable, it will proceed with that rearrangement. So we are going to be talking about carbocation rearrangements, which, as you might expect, involves rearranging carbocations to make them more stable. So if I have a secondary carbocation, it may rearrange to become a tertiary carbocation if that is possible. And I will show you some examples of when that can happen. Now we have two main types of rearrangements. We have this hydride shift, that's where a hydrogen moves. So movement of H. And then we have this alkyl shift, and that's a movement of an alkyl group. So movement of R group. R group is really the word here. Movement of some R group. And usually this almost always tends to be, usually, not always, but usually tends to be a methyl group. Okay, so a CH3 group is usually the one that we expect to shift, to rearrange. Okay, so hopefully this gives us a pretty decent overview of what we can expect. So now let's go ahead and look at some examples here. I'm going to start with the hydride shift, and then I'll move on to the alkyl shift. So in looking at this example here, I have this alkyl halide, and the first thing I'm going to notice here is that this is a secondary alkyl halide. Okay, this is a secondary halide. If you've seen my videos in the past, you know that the first thing that I always like to do is look at what kind of alkyl halide I have. And here I have a secondary one. Now I am reacting this alkyl halide with ethanol, ETOH, it's ethanol, looks like this. And I'm reacting it at 0 degrees Celsius. 0 degrees Celsius usually means substitution. Usually colder temperatures mean substitution. So if I have a secondary alkyl halide and I'm using a weak nucleophile, I can pretty confidently assume that this reaction is going to be an SN1 reaction. Okay, this is an SN1 reaction because I have a weak nucleophile, cold temperatures, and a secondary alkyl halide. The weak nucleophile is really the big thing here. This is a weak nucleophile, and the colder temperatures is like icing on the cake. So we're going to analyze the mechanism here that we would expect the same way we would do for any sort of SN1 mechanism. And if you remember from my earlier videos, the first step in any SN1 mechanism is for the leaving group to leave. So that bromine has to fall off. We see that with the bromine with the negative charge, has these lone pairs. So that leaving group has left. And remember, when the leaving group leaves, we observe this carbocation intermediate. Okay, so we have this carbocation intermediate. Now, I've written it out here. This carbocation, I'm going to highlight it in blue, that's a secondary carbocation. Now, a secondary carbocation, if we go here, secondary is right here. So it's not unstable, like super unstable. It's not exactly incredibly stable either, but it's not ridiculously unstable. It is in the latter half of this series. However, I have this carbon that is adjacent to it, and this carbon has this hydrogen on it. Now you'll recognize that this carbon right here, I'm gonna label this. This is a tertiary carbon. This carbon has 1, 2, 3 R groups attached to it. So what can happen in this type of scenario? If I have an adjacent carbon that is more stable than the carbon that I'm working with, for example, this one is a tertiary carbon, and this carbon that I have here, this is secondary, what I will observe is that if I have an available hydrogen, like I do right here, that hydrogen and the lone pairs of that carbon-hydrogen bond, they are going to literally shift over. So I'm just going to take this and I'm just going to pick it up and move it. Okay? That hydride is a hydrogen with a lone pair and a negative charge. That hydride is literally picking itself up and moving to go to the carbocation. So if I see here, that hydrogen that was on this tertiary carbon, now it's on that secondary. Now it's on that secondary carbon. Now it's there. So that hydride has picked itself up and moved itself over. What this is going to do then is the carbocation is going to shift over to the adjacent carbon. So my carbocation that was at this carbon, it is now at this carbon. And we said this was a tertiary carbon, so this is a tertiary carbocation. And we know from our series that a tertiary carbocation is far more stable than a secondary carbocation. So what we observe is that this hydride shift has occurred to make this carbocation more stable. Hence why we observe us going from a secondary carbocation to a tertiary carbocation. And now that we're at this carbocation, now we can proceed with our SN1 mechanism the same way. We would attack the carbocation and then we would lose a proton. I'm not going to go through all the details of this mechanism, but we would lose a proton. And our end product would be something that looks a little bit like this. Okay, something that looks a little bit like that. And you'll recognize here that this ethoxy group is not on the same carbon as this bromine group. That's because we had this hydride shift that occurred in the middle of the mechanism. The molecule very briefly rearranged. So that is a hydride shift. Now we can expect something similar with an alkyl shift. So I'm going to take a similar carbocation, or similar alkyl halide. This is again secondary halide. I'm also reacting it with ethanol, and this time I'm reacting it with heat. So ethanol with heat, secondary alkyl halide, this is an E1 reaction. These are classic conditions for an E1 reaction. Ethanol is a weak base, so E1. Again, same deal with the mechanism. The bromine is going to leave first. I'm going to get this bromide ion. And I get, again, this secondary cation. Except this time, the carbon that we were just talking about with the hydride shift, this was a tertiary carbon. This is a quaternary carbon. So this is a carbon that has 4 other R groups. But just like last time, the departure of this leaving group leaves us with this secondary carbocation that is adjacent to this quaternary carbon. And this quaternary carbon is able to shift a methyl group. Okay, is able to shift a methyl group or a hydride, but there is no hydride at this quaternary carbon. It's just 3 methyl groups and then this whole thing. So instead of shifting over a hydride, I'm just going to shift over an entire methyl group. Okay, the same sort of logic that we just observed here is happening here. It's the same logic. All I'm changing is which group is shifting. So here I am observing a methyl shift. And that's going to give me a tertiary carbocation yet again. And here I have a couple of options. Because this is E1, I'm going to favor the most stable alkene. So I'm just going to use this. I'm going to pick up this proton, and I'm going to make that pi bond right there. So what I end up with, something that looks like that. So that's my alkene. But you'll recognize here, again, that this carbon originally had 3 methyl groups on it, and now that same carbon only has 2. And if I come over here, this carbon initially had 2 methyl groups and nothing else. Now it has 2 methyl groups and that ethoxy group. So the last point I'll make about these is how to identify them. And that little bit that I did at the end there, that's a good way to identify these. If you see a molecule that starts off like with this carbon, this carbon here started off with these 2 methyl groups, I have that methyl group and I have something else extra there, right? The molecule looks like it has moved around. That is a pretty good indicator that a carbocation shift has occurred. Same deal here. If I have an alkene and I realize that I can't make an alkene with that carbon because I don't have any beta protons, but then there is a double bond at that carbon, that is indicative that something has shifted, something has rearranged. So if you observe any of that, that is a pretty good indicator that a carbocation rearrangement has occurred. And again, in most undergraduate courses, this is pretty much exclusively limited to hydride shifts and alkyl shifts. Alright, so I hope you found this video helpful on carbocation stability and rearrangements. This is an important topic that will continue to show up in your OChem courses, so I wanted to make one very comprehensive, in-depth video of how this works. If you have any feedback, I would love to hear it in the comments below. Please do leave a like and subscribe for more OChem content. I look forward to seeing you in the next video. Take care.